This is a lecture from Open Tuition. For the free lecture notes that go with this podcast, please visit opentuition.com. This is the first of two lectures on Chapter 11 of the Paper F5 course notes, which is Quantitative Analysis in Budgeting. Now you'll see in this chapter there are three techniques, each of them completely separate, but three techniques that can be useful when people are preparing budgets. And each of these three techniques can form a major part of a Paper F5 question. Now I've listed the three techniques on the screen. There's something called regression analysis, which you should have done before. It was in the Paper F2 syllabus, and there's nothing extra on this at Paper F5. And so, as I say, you should have covered it, whether it was at Paper F2 or at university. The second one is something called time series analysis, which is new. It wasn't in F2. And similarly, the third one, learning curves, again, wasn't in Paper F2. Now, I'm not going to go through regression analysis because it should be revision for all of you. If for any reason you haven't done it before, or you've done it but you've forgotten it, then look at the Paper F2 section on the Open Tuition website and you'll find a lecture there, and so use that. But I'm not going to go through it again for Paper F5. The other two I will go through. In this lecture, as I say, it's the first of two. In this lecture I'll go through learning curves, which is certainly the most important of the three. And then in the second lecture on Chapter 11, I'll go through the other one, time series analysis. So let's make a start on learning curves. And first of all, let me explain briefly what it's about. Just suppose my company was going to start producing desks. We've never produced them before. It's a new product. And of course I need to estimate what the cost is going to be so that we can fix a selling price. And so I need to do a cost card. How much is it going to cost to produce one desk? Now the obvious thing to do is to experiment. Let's make one desk, and if we can work out how much that desk costs, then no problem. I've got my costing. I can go ahead and start estimating a selling price. But we could do a cost card, and I'm making up some figures here. Ignore the notes at the moment. But we could do a cost card for desks. We've done enough cost cards in earlier chapters. And materials, in theory, they shouldn't be a problem. We can make a desk. We can measure how much material we use. You know, maybe it uses 2 square meters of wood. Wood maybe costs us $5. No problem. But where the huge problem comes is labour. Now there's the big problem, because remember, we've never made desks before. This is a new product. And I'm sure if I asked you to make a desk, assuming, whoever's listening, assuming you've never made a desk before, it's likely to take you a long time. You know, maybe, as I say, I'm making up figures here, but maybe it takes you 50 hours to make a desk. Maybe I pay you at the rate of $10 an hour. Easy arithmetic. And then we could carry on and add on overheads. But the problem is this. Although the first desk, this one desk we've made, maybe takes 50 hours of labour, it's the first desk you've ever made. And if I carried on and asked you to make a second desk, a third desk, a fourth desk, surely for something like that, the chances are you'd get faster and faster the more desks you made. There is going to be a limit, obviously. You know, you're not going to make desks instantly, but it may be by the time you've made a few hundred that you're taking only 2 hours a desk. And surely if we intend when we produce this desk to start producing thousands of them, well, Again, the first few may take an awful long time, but in a sense that's just a development cost. If, as I said, by the time you've made 100 or so, you're doing it in 2 hours, then surely the long-term cost is only going to be 2 hours a desk. And I should base my selling price on the long-term cost when I'm producing thousands, not just on the first 50, the first 100, whatever it is, which, while you're learning, while you're getting faster, which, as I said, is more of a development cost. So that's the problem we're talking about. The first desk may well take us 50 hours, but what I really need to know for my costing is how long will it take when we're in full production? How am I going to work out that 2 hours in my little example? Well, for learning curves, there is a rule. There's a rule which lets us estimate. If we know how long the first desk takes, it lets us estimate how long it'll take for the second desk, the 10th desk, and so on, as we get faster. Now, the rule itself is printed on page 62. If you turn to page 62, paragraph 6.2 is headed up Theory, and there is the basic learning rule. As the cumulative output doubles, the cumulative average time per unit falls to a given percentage of the previous average time per unit. Now, that's fine, but we can read that 10 times and it still not make sense. So let me show you with example 6, again page 62. Let's look at example 6 and let me use that to explain how the basic learning rule works. You shall see there's a little problem with it which we'll deal with later, but a simple little example to explain, as I say, the basic rule. So example 6, it says the time taken to produce the first unit is 100 hours. There's a learning rate of 75%. Now we'll discuss later where that may have come from, but in the exam, if you're told the learning rate, your job is to show how it applies, but it's effectively, as you'll see, the speed of learning. Now the actual question says how long will it take to make an extra 7, but let me first of all use that little example just to show you how the rule works. Now how you set this out is up to you. I'm going to do it as a little table, which I think is the safest, the neatest way. What we do is this. If we make 1 unit, I'm leaving a space here, but the total time for that 1 unit in hours is what? 100 hours. Now, it may seem a little bit silly for the moment, but surely if you're making 1 unit and it takes 100 hours, the average time per unit at the moment is again 100. As I say, that may seem a little silly for the moment, but shortly it'll become important. Well, what the learning rule says is that if we double the production, and by double it, we've made 1, double it 2 times it, if we make another 1, so we've got 2 in total, so we've doubled the production by making an extra 1. What the learning rule says is that the average time per unit will fall. It'll fall to a fixed percentage of what the average time was before. So what I mean is this. Make 1 unit and the average was 100 hours. If we double, make another 1, so we've made 2 units in total, the average time per unit will fall. It'll be 100 times whatever the learning rate here is. Here it's 75%. Well, 75% of 100 is 75. Now, arithmetically, that's easy, but very importantly, that 75 is not the time of the second unit. What that 75 is, it's the average time per unit if we make 2. And so we need to do a little bit more work. I'm saying if I make 2, on average they take 75 hours each. So how long in total? 2 units at an average 75 is 150 hours. And so we now know that to make 1 unit took 100 hours, to make 2 units takes 150. So surely the difference between the two, 50 hours, that is the time for the second unit. And so do be careful. It's amazing how many people half learn the rule and do silly things. It's not hard arithmetic. But the learning rule does not give you the time for that second unit directly. It tells you what will happen to the average time. If you know the average time, we know the total time. And by subtracting, by looking at the difference between the time for the first, the total time for 2, then we can get the time for the second. And that rule continues. So we've now made 2. Suppose we double again. We've made 2, let's make an extra 2, which doubles up to 4. Well, of course, each one gets faster and faster, but all the learning rule will do is tell us what the average time per unit is when we make 4. It's 75% of the previous average. So 2 was on average 75. 4, 75% of 75 is 56.25. But again, as I keep saying, that is not the time for any one unit. The first took 100, the second took 50, the third will be faster, the fourth will be faster. But that's the average time per unit if we make 4. So the total time for 4 units, 4 times the average, is 225. And I can go one step further. Remember, we knew that 2 units took us in total 150 hours. Make another 2 units, and in total we've now spent 225. Well, the difference between the two of 75 hours. It's the total time for the third and the fourth. And immediately there's one problem with the basic rule, that the basic rule won't tell us how long number 3 took or how long number 4 took. You know, maybe number 3 took 45 hours, maybe number 4 takes 30 hours. It won't tell us. All it tells us is that in total, those next 2, number 3, number 4, in total took 75 hours. But with that limitation, we can carry on forever. Let's carry on just one more. Let's double again. We've made 4. Let's make another 4, so we've now made 8. The average time if we make 8, 75% of what it was before. Is 42.1875. Now don't worry, a bit of rounding here won't be a problem, but here I'll keep it precise. But again, 8 units on average take 42 hours each. The total time, multiply by 8, is 337.5. And again, I'm not going to write down, but the time for those extra 4 in total will be the difference between 337 and 225. But the basic rule will not tell us how long for number 5, number 6, number 7, number 8, just how long they take in total. Well, we could carry on that forever, keep doubling. I'm not going to, but we could do it for 16, for 32, and so on. However, that's the way the rule's working. But let's now answer the actual question in example 6. It actually said, how long will it take to produce an additional 7 units? The question itself, we've made 1, remember? How long will it take for an extra 7? Well, of course, if you've made 1, an extra 7 means you've made 8 in total, and I know how long it takes for 8. However, I'm going to write it out again because although we've got the answer more or less in front of us, in the exam you don't want to waste time doing step by step by step as I did. That was simply to explain the rule. And also, when we extend it in a moment, then what I'm about to do becomes very important. If ever you get a question like this, and it is likely, the way to approach it is as follows. How long will it take to produce an extra 7? Well, you can never get that in total, but the way we do it, we say, we've made 1, an extra 7 makes 8, so we're going to work out the total time for 8, and if we can work out how many hours 8 units take, well, if we deduct the time for the first, then surely it'll give us the total time for the next 7, which is what we want. Well, the time for the first, obviously we know we're given it's 100 hours. The total time for 8, well, as I hope I've already made clear, you can never write it straight down. It's always 8 times the average time. The learning rule lets us work out the average time per unit. The total will be 8 times the average. How can we work out the average time? Well, fortunately here it's doubling, and we just did it. We knew the time for 1 was 100. The time for 2 was 75% of 100. Double it to 4, it was 75% of that. Double it to 8, it was 75% of that. And of course we've done it. I'm not going to write down all the arithmetic again. But taking 75% each time gave us, I've lost it again, 42.1875. And having got the average time, the total time for 8 times 42.1875 is 337.5. And therefore the time for the next 7, which is what we're after, (237.5 hours. Now I know that was very much repeating what I'd already done. I'm just saying there are two things. Understand how the doubling rule works. That could be asked on its own as a little written part. Explain the doubling rule. So do understand how it works. If they do ask you a question, which they have done in the past, like example 6, how long for the next 7, then approach it the way I've done on the screen at the moment. How many in total? Total time, the number 8 times the average. Deduct the time for the first, and we've got the time we're after. Well, I hope that makes sense. Again, it's not, I've said before, it's not hard arithmetic. Just make sure you've got it straight. People do make the most stupid mistakes, and it's such a shame when the arithmetic's easy. However, it's probably already occurred to you there is one big problem. That works fine when we're doubling. So another 7 took us to 8. 8 is doubling, absolutely no problem. Provided it's 2, 4, 8, 16, 32, whatever, we can do this. But what happens if I'd given you example 6 and said, we've made 1 unit, how long will it take to make another 5? Well, of course, another 5 would mean 6 in total. And the basic rule, we won't be able to do it for 6 because that doesn't involve doubling. We are stuck with 2, 4, 8, 16. And so, although you must know the basic rule, he can test you on the doubling rule. In fact, we can deal with any number even if it's not doubling. But for that, we need a formula. Now, you'll see the formula on the next page under paragraph 6.5. For the moment, ignore it and don't worry about it. I'll explain how it works. Let's, though, look at example 7. Flogel has just produced the first full batch of a new product, taking 200 hours. The learning curve effect, the learning rate, this time is 85%. Question A, how long will it take to produce the next 15? Well, that we can do, surely. So forget this formula for the moment. In that if we've made 1 and we make another 15, that means we've made 16 in total. And so, just like before but with different figures, to get the time for the next 15, if we work out the total time for 16, if we deduct the time for the first, then we've got what we want. And of course, like before, we know the time for the first one. This time it's 200 hours. We need the time for 16, but 16 is doubling. 2, 4, 8, 16. So have a go yourself. Using the doubling rule with a learning rate of 85%, how long will 16 take? Well, hopefully you have paused the lecture and had a go, but check with me now. The time for 16, it'll be 16 times the average time. To get the average time, we'll double. So a bit of workings. The first took 200, so the average time was 200. Double up to 2 in total, and the average time is 85% of 200, which is 170. Double again to 4. 85% of 170 is 144.5. Double again to 8. 80% of 144. Sorry, 85% of 144.5. And finally, double again to 16. And of course, if you're keeping the figure in your calculator, there's no particular need to round. I said earlier, if you round it, no big problem. But there's no particular need if you've kept it in your calculator. But the average time is 104.40. The total time, multiply by 16, and I get 1670.42. Now that's the total time it'll take to make 16. Again, the first one was 200 hours, so the total time for those extra 15, 1470.42. So there's doubling. We've done it twice. If you need, go back and make sure. But I say again, formula or no formula, you certainly could be asked and have been asked specifically to do the doubling. However, although no problem hopefully with part A, part B, there is a problem. Read it with me and make sure you understand precisely what's being asked, first of all. Same question, that we've produced one batch, 200 hours. We know we're going to get faster and faster. Each unit gets faster, but it says that after the 30th has been produced, the learning will stop. Think about it in real life. Produce desks, you will expect to get faster and faster, but not forever. There will be a limit when you're going as fast as you can. Now, for whatever reason, we think that after we've made 30, we'll stop learning, and therefore from the 31st onwards, each batch will be the same time as the 30th. And it says what time should be budgeted. So surely if it turned out that batch number 30 took, let's say, 5 hours, then from then on every batch will take 5 hours, and it's 5 hours we'd use in our budget. So how are we going to work out how long number 30 will take? I've already said in the previous examples you can't get any one directly, but we are going to be able to work out the total time to make 30. I'll show you how in a minute, but we are going to work out the total time to make 30, and like the previous ones, to get it, we'll have to work out the average time. The total will be 30 times the average time per unit, or here per batch. Now that'll give us the total time to make 30. To get how long number 30 itself took, if we deduct the total time for 29, the difference will be the time for number 30. And how can we work out the total time for 29? Same rule as always, it'll be 29 times the average time. So far, just the same, exactly the same approach as the previous two, but now we hit the problem. If the total time for 30, if 30 was doubling, we can get the average time using the doubling rule. But I hope clearly neither 30 nor 29 involve doubling. We can't use the doubling rule, but there is that formula. Now you get the formula on the formula sheet, and you'll see a formula there in paragraph 6.5 above the example. A formula, y equals ax to the power b. And what that formula gives you, and if you look on the formula sheet incidentally, here you are told what the symbols mean. It says y is the average cost per batch. Now in fact, I'll explain later, you can do it on costs, but more sensibly, y is the average time, which is what we're after. Just like doubling gives you the average, so too does the formula. A is the time for the first. I'll fill in all the figures properly in a moment, but for this one it's what? Example 7. I've lost which example we're on. Here we are, example 7 is 200 hours, no problem. X is the number of units or batches. Again, in a moment, no problem. The one place there is a little problem is B, and B has its own formula. Now, to be honest, the chances of needing the formula for B are almost impossible. In the exam, if this is needed, then in the question, almost certainly you'll be given a value for B. But he would be allowed to ask you to calculate. And so you'll see, again, in paragraph 6.5, B is the log of R over the log of 2. And again, it is given you on the formula sheet. Although, as I say, it is very unlikely you'd need it. Now, immediately, logs. Logs are something you should, I think, have covered at school. But whether you did or didn't, or whether you remember or you don't remember, to have a lecture on logs here would be silly. It's the only place in the whole of ACCA where it just could be relevant. Even then, it's very unlikely. And, well, for other reasons here, you've got to have a scientific calculator. And if you have a log button, then to be honest, it's irrelevant what log means. It's just a question of using it. So let me show you with this example. Let's work out b first of all. It's log of r. Well, r is the learning rate, which here is 85%, but written as a decimal. So instead of 85%, it's 0.85 divided by the log of 2. Now, calculators work in different ways. You know, it depends which calculator you've got. So if you need, I'm afraid you're going to have to look up in your instruction booklet. But on my calculator, all I do is this. Log of 0.85, I put 0.85. I've got a button that says log on it. I press that. And I get minus 0.070581. Now, so you're going to have to practice on your calculator and sort out. Some calculators, you press the log button first. Others, like mine, you press the number first. Do note it's negative. In a moment, that'll be important. You might remember from school, the log of any number less than 1 is negative. The calculator shows it negative, and it will matter. We divide it by the log of 2, so again on my calculator, 2 log 0.30103. Now, if you're efficient and you're able to use your brackets on your calculator, you don't need to write all the figures down. But it actually comes to, let me do it again, I beg your pardon, 0.85 log divided by 2 log. It comes to minus 0.2345. Now, I said earlier, if this is needed in the exam, then it's very unlikely you'll be expected to use the formula. You'll probably be given B, and of course if you are given B, don't waste time checking it. Use this figure. We normally, if you have got to calculate it, we normally just leave it to four decimal places, as I've done. But critically important is that it is always negative, always. If he gives it, there'll be a minus sign there, but don't forget it. If you're having to do it yourself, the calculator will come out with a negative answer, but it will be vital in a moment. Having got B, though, now we can use the main formula. Now, in fact, as you'll see, I'm going to have to use it twice because, first of all, let's work out the average time if we make 30. Average time for 30. The formula is y equals ax to the power b. Well, y is the average, that's what we need. A is the time for the first, 200 hours. X is the number of units or batches. Well, we're doing it for 30. To the power b to the power minus 0.2345. Now, this bit you're certainly going to have to do yourself. And I'm afraid, again, you are going to have to experiment with your calculator if you need, or look at the instruction book, because different calculators, you input it different ways. But I'll tell you slowly what I do on mine, but I do warn you, not all calculators do it this way. I want 30 to the power 0.2345. Now, I'll write down the buttons I press. I go 30, so obviously 3, 0. I then have a button that says x to the power y. So I press that. I then go 0.2345, but importantly, for the moment, no negative. So I'm not going to write down each button, but 0.2345. But I've then a button that says plus stroke minus on it, and I press that, and you'll see it now shows minus 0.2345. Then I press the equals button and I get, hopefully the right answer, yes, 0.450. I'll leave the rest of it in my calculator. I'm not going to write it down. But of course then I can multiply it directly by 200 and I get 90.08. Now, practice that yourself. I know I keep saying the same thing, but the trouble is different calculators use a different logic. With other calculators, you put things in a different order. So check if it works my way on your calculator, fine. If it doesn't, practice, but make sure you can do it. It's awful to be able to do everything else right, but end up with the wrong answers simply because you can't use your calculator. I've said many times in these lectures, I really do suggest you pause the recording, that you check that you can do that yourself and get the same answer, and then you try yourself working out the average time if we make 29. Obviously I'll do it here using the formula. It's a time for the first. This time x is 29 to the power b. 29 to the power minus 0.2345. 29 x to the y 0.2345 plus minus equals, I get 0.45401. I wouldn't normally bother writing it down, to be honest. I'd keep it in my calculator, but multiply by 200 and I get 90.80. Finally though, for this example, do please remember that all you've worked out for these two is the average time per unit. If you look back at the table we set up, what we need to know is the total time. So making 30 will be 30 times the average time, which was 90.80. The total time for 30, therefore, 2724. Similarly, the time for 29. 29 times the average. The average when we made 29 is 90.8. Giving total 2633.2. And finally, remember where we are. To make 29 will take 2,600 hours. Sorry, I must have made an arithmetic mistake. 29 times 90.8. I do apologise. I got them the wrong way around. I am sorry. It was 90.08 when we made 30. It was 90.80 when we made 29. So now let's do it. 30 times 90.08. Total time for 30 is 2702.4. Total time for 29, 2633.2. And what I started to say, but remember, it's 2,600 hours to make 29. To make 30, 2,700. Well, the time for number 30 must be the difference of 69.2 hours. And there we are. Remember, we're saying, if you look back at the question, that for all future units, we may make tens of thousands of them, but they'll all take 69.2 hours. And so on our cost card, we'd bring in a time per unit of 69.2 at whatever the cost per hour was. All right, well, I'll leave this lecture here, but as I said at the beginning, there'll be a second lecture on chapter 63 covering time series analysis.